Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Introduction to Energy. We'll be discussing kinetic energy and potential energy, and within potential energy, both gravitational and elastic forms of potential energy. As always, please be an attentive learner as you watch this video. As an introduction, I want to talk a little bit about what we've done. We've started out talking about units, and we said in physics there are units of time, which is a seconds, lengths, which is meters, and mass, which is kilograms. And then we started deriving units. So we said, well, meters per second gave us velocity. But now we started talking about something that is a vector quantity. And so that it becomes velocity, but with the arrow on top, that is a vector quantity. But then we had another derived unit. We took velocity per unit time, change in velocity per change in time, and we called that acceleration. And again, that was a vector quantity. And most recently in the lectures, what we did is we took acceleration and mass and started talking about a quantity called force. And we had Newton's 3 laws of motion having to do with force. This force vector will be a basis for many of the things that we'll talk about later, and that will find application in your field of ultrasound. Okay, so we talked about Newton's 3 laws, and in this chapter, though, we'll introduce a new concept. And this is going to be energy. It's going to be built on force. This is one of the most important unifying concepts in all of physical science. Its importance stems from the fact that energy can neither be created nor destroyed, but it can be transformed from one form into another. The principle is known as conservation of energy. In this chapter, we'll concentrate on mechanical energy, which is associated with motions and positions of mechanical systems. Initially, we'll tour the main ideas associated with energy on a qualitative level, and then we'll develop the concepts of work and kinetic energy, energy of motion, and the relationships between them. In the remainder of this chapter, we'll learn how to apply these concepts into the analysis of problems. We can think of energy as a measure of a system's ability to interact with and change its surroundings. For example, a nut falling from a tree has relatively little energy, and consequently it does virtually no damage to your car if it hits your car. However, a brick dropped from a tree is another matter. It has much more motional energy and can do much more damage. The concept is the cornerstone of a fundamental law of nature called conservation of energy, which states that the total energy in an isolated system is constant. Conservation laws, including conservation of mass, energy, momentum, angular momentum, electrical charge, and other quantities, play vital roles in every area of physics and provide unifying threads that run through the entire fabric of the subject. Every conservation law says that the total amount of some physical quantity in every isolated system is constant. Something analogous happens in collisions between objects. When two hard, springy objects, such as steel ball bearings, collide, the individual speeds change, but the total energy remains nearly the same as before the collision. This energy of motion is called kinetic energy. Kinetic means motion. When it is exactly the same after collision as before, we say kinetic energy is conserved. And here is the definition of kinetic energy. An object of mass m moving with a speed v, and that's actually a velocity v, has an intrinsic energy of motion called kinetic energy, and kinetic energy is denoted by K, where K is equal to 1/2 mv squared. Now, energy and kinetic energy is not a vector, so even though it has a velocity, the speed is the magnitude of this vector. So it's just 1/2 mv squared. The units here are called joules. They're named after a great scientist named Joule. And if you look at this, you can see that the kinetic energy is going to be 1/2, which has no units. This is going to be kilograms, and that's going to be meters per second whole squared. So a joule is a kilogram meter squared over second squared, or kilogram meter over second whole squared. But you see a kilogram meter per second squared is m times a, or a newton times a meter, or this is force times distance. It's going to be useful for you to remember this equivalence here. Note that kinetic energy is a scalar and is always positive or zero. And K, the kinetic energy, can be transformed from one form of energy into other forms of energy. For example, nuclear energy is at the sun's core, but this becomes energy of the sun's hot gases, which becomes energy of the sunlight, which is converted by plants into chemical energy of grains and other foods. And when somebody makes that into a sandwich and eats the sandwich, you consume as calories, and calories can help you give you the energy, which can be used to lift weights, and the story goes on and on. The point is that this is a sequence of energy transforms and transformations, and this happens over and over again in science. We've talked about kinetic energy. Let's talk about another class of mechanical energy that we'll consider. And this is energy that is not directly associated with motion, as kinetic energy is, but rather a quantity that is stored as a result of a position or elastic deformation of an object. As an example, consider the rubber band down here in the slingshot. You put a stone in here and you pull it back, and then when you release it, the stone starts moving. So you see there is potential energy that is stored here. So consider the stretched rubber band of a slingshot. You have to expend energy to stretch it, and as soon as it's stretched, physical changes occur, and the slingshot projectile could fly across the room. An unstretched rubber band lacks this capability, but the act of stretching it stores energy into it. Releasing the rubber band allows the stored energy to be transformed into other types of energy, such as kinetic energy. We call this stored energy potential energy. Energy that is stored in an elastic object when you stress, compress, twist, or otherwise deform it is called elastic potential energy, and this is an example of such elastic potential energy. Another example of potential energy is the skateboarder that we see here. When he descends from the top half of the half pipe, he speeds up and gains kinetic energy. In fact, if you look at this, he's not moving at all up here, and so his kinetic energy is zero. But then he starts going down, he starts moving, he gets a kinetic energy. And so this gravitational potential energy up here is changed into kinetic energy as we go down, and he goes faster and faster, but then he starts going slower and slower, and what happens is the kinetic energy is being changed back into gravitational potential energy, and he could jump off over here, and if that's the same height, he would have changed the gravitational potential energy into kinetic energy and back into gravitational potential energy. Whenever an object moves vertically, while the gravitational force, its weight, acts on it, the gravitational potential energy changes. The greater the height, the greater the change in gravitational potential energy. Soon we'll have a formula for this, and it's going to be mg times h. Kinetic energy, elastic potential energy, and gravitational potential energy are all forms of mechanical energy. There are other kinds of energy, heat energy or thermal energy as examples. So there's a problem for you to consider, breaking the speed limit. How much more kinetic energy does a 1,500 kilogram car have when it's traveling at 90 miles per hour than when it is traveling at 70 miles per hour? And you must be conscious of units as you're doing this. So it's a multiple choice question. You know what to do. Let's see how you did. All right, you need to calculate the kinetic energy for each speed, and these were in kilojoules, megajoules, and well, kilojoules in A and D, and megajoules in B and C. But we have kilograms here, which is fine, but we have to change 90 miles per hour and 70 miles per hour into meters per second to get them into these units. So 90 miles per hour is changed into 40 meters per second, and 70 miles per hour is changed into approximately 30 meters per second. And so the difference in kinetic energy, delta K, is equal to the kinetic energy of the faster car minus kinetic energy of the slower car, or the car moving at a different speed, and you get it as 0.48 megajoules, and the closest to that is number C. So the correct answer is C to this problem. Now, there is an analogy between energy and money. And how is money like energy? Well, it can take multiple forms, just like money can have different forms. You can transform it from one form to another. These transformations do not change its total amount. You can transfer it to change the total amount. It can be stored or it can be spent, just like money. Let's do a physical example showing that, not with money or an analogy, but really with this. So suppose you took a stone and stretched it using a slingshot. And so what happens is that your energy goes into and makes this into potential energy. And this is elastic potential energy. But then you release it. Well, what happens is your elastic potential energy of the sling is converted into kinetic energy of the rock. And you have a velocity. So you start out with a velocity and kinetic energy. And the kinetic energy is 1/2 m, the mass of the rock, times v squared. The rock is rising. Now, when the rock is rising, what happens is it starts out with all kinetic energy, but then it's going up, and so the kinetic energy of the rock is converted to gravitational potential energy. It goes slower and slower and slower, and eventually it reaches the top of its trajectory. And here, it has gravitational potential energy only because it's changing from a positive velocity to a negative velocity. So right here the velocity is 0, which means that it has 0 kinetic energies. Then this energy starts changing again, and this gravitational potential energy that was gained from here to here starts being changed to kinetic energy as it goes faster and faster. And if it hits your car, it would hurt your car. Depending on what kind of a stone it was, I suppose. So as the rock is falling, gravitational potential energy is converted to the kinetic energy of the rock. Mechanical energy can be dissipated also. Sometimes it can go into heat or other thing. And so any forces such as friction that turn mechanical energy into non-mechanical forms of energy is dissipative force, because it dissipates or reduces the mechanical energy. And so non-mechanical energy can also be converted into mechanical energy. An example of that is when a car's engine does when it converts the internal energy of a combustion into the motion of the pistons in your car. Now let's summarize then the key points we've established in this session. Energy can take on various forms. Here we've concentrated and will continue to concentrate on kinetic energy, gravitational potential energy, and elastic potential energy. These are all mechanical energy. The total energy is always conserved, but it can be transferred among them. And mechanical energy can be dissipated to non-mechanical forms and vice versa. And that's the same chart as we just looked at. So in closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.